Week 4, Sampling and Sampling Distributions. Picture this. Someone hands you a box of 3,000 supplier receipts and asks you one question. Is the average value over 50 ringgit? You have one afternoon to answer, not 1 week. You would not read all 3,000 receipts. Nobody would do that. What you would actually do is grab a reasonable handful, add it up, and use that handful to make a confident statement about the whole box. And here is the interesting part. You already trust this instinct in dozens of situations that have nothing to do with receipts. When you taste a spoonful of soup before serving the whole pot, you are not tasting every drop. You are trusting that one spoonful tells you something true about the entire pot. When a pollster wants to know how an entire country plans to vote, they do not call every single voter. They call a few thousand and trust that those few thousand tell a true story about millions. When your doctor wants to know whether you have a particular condition, they take one small vial of blood, not all of it, and trust that vial to represent everything happening inside you. That instinct, the idea that a small, well-chosen piece of a group can honestly represent the whole group, is the entire subject of today's lecture. Auditors do this every single week. Accountants do this every closing period. Quality control teams do this every single day on a factory floor. Doctors, pollsters, and market researchers do it constantly. We have simply never sat down and asked exactly how confident we are allowed to be when we do it, and exactly how to defend that confidence with numbers instead of just a gut feeling. So today, we are going to slow that everyday instinct down to its individual moving parts. We are going to attach precise language to each part, and we are going to add a little bit of careful arithmetic underneath all of it. By the end of this lecture, I grabbed a reasonable handful will have turned into something you can actually defend out loud in a written report, in front of a partner at your firm, or in front of a regulator asking hard questions. Let's get into it. Good morning, everyone, and welcome back. This is week 4, and our topic is sampling and sampling distributions. I want to be upfront with you about something before we even begin. This is a genuine turning point in the course. Almost everything we do from this point forward in the semester depends directly on the ideas we build today. So even if you are feeling tired, even if this particular lecture is a repeat for some of you sitting here, I am going to ask you to stay with me closely for the next while. It is going to pay off, I promise you that. This slide lists 8 specific things you should be able to do once we finish today's lecture. I am not going to ask you to memorize this list right now. Think of it more like the map you glance at before a road trip, just so you know roughly where the road is going to take you. Here is that trip, described in plain, ordinary language instead of formal objectives. We are going to learn how to separate a whole group of interest from a smaller piece of that group. We are going to learn 4 organized, disciplined ways of picking that smaller piece, and then 4 looser, more informal ways of picking it. We are going to meet a rule with a slightly intimidating name, the central limit theorem, which turns out to do an extraordinary amount of heavy lifting for us. And by the end, we are going to build something called a confidence interval, which, despite the technical sounding name, is simply a range of believable values with a percentage of trust attached to it. Does that sound like a reasonable itinerary for today? Good. Let's start driving. This slide shows the timetable for what is normally taught as a full 4-hour class, broken into 4 parts labeled A through D. Since we are recording this as one continuous lecture rather than a live 4-hour session, I want you to think of A, B, C, and D simply as 4 chapters inside one continuous story rather than 4 separate, disconnected lectures. Chapter A is going to cover populations, samples, and the formal, organized sampling methods that statisticians trust the most. Chapter B is going to cover the less formal sampling methods, and then introduce a brand new idea called the sampling distribution. Chapter C is really the engine room of the entire lecture, where we meet the central limit theorem and build our very first confidence intervals. And Chapter D covers a backup tool we reach for when we have more limited information, plus a practical walkthrough of doing all of this in Excel and in SPSS. As we move through the lecture, listen for those 4 letters, A, B, C, and D, as signposts marking where we are along the way. Let's do a quick rewind, because today builds directly and deliberately on what we covered last week. Last week, we met the normal distribution. A normal distribution is a smooth, symmetric, bell-shaped curve where values near the middle happen often, and values way out at the extremes happen rarely. Think about something like adult height in a large population. Most people cluster around an average height, A smaller number are noticeably taller or shorter than that average, and almost nobody is extremely far from it in either direction. That clustering pattern, common in the middle, rare at the edges, is what a bell curve actually looks like. We also learned how to standardize a single value into something called a z-score. A z-score simply counts how many standard deviations a particular value sits away from the mean of its distribution. Every probability we calculated last week was about one single observation at a time. One height, one test score, one measurement. Today, the question changes in an important way. Instead of asking about one single observation, we are going to ask what happens to the average of an entire sample if we imagine drawing that sample over and over and over again. That shift from thinking about individual values to thinking about averages of groups of values is the question that drives the rest of this entire course. Does that make sense so far? Good, let's keep going. Welcome to Part A, Population, Sample, and Probability Sampling. This is where the brand new vocabulary for the course really starts, so stay close with me here. Here are the two most important words you will hear in this entire course. The first word is population. The second word is sample. What is a population? A population is the entire group that you actually care about and want to draw a conclusion about. A sample, on the other hand, is the smaller part of that population that you actually observe, measure, or look at directly. Let's make this concrete with an example you will recognize from daily life rather than from a textbook. Suppose you want to know the average commuting time for everyone who works in a large city. Every single commuter in that city, all of them together, is your population. Now, you obviously cannot interview every single commuter in the entire city. That would take forever and cost a fortune. So instead, you might survey 500 commuters chosen carefully from across the city, and that group of 500 is your sample. Here is another way to picture the same idea. Think about a chef who has cooked an enormous pot of soup for a banquet hall full of guests. Before the soup goes out to every single table, the chef tastes one spoonful. The entire pot of soup is the population, the one spoonful the chef tastes is the sample. Nobody eats the whole pot just to check whether the seasoning is right, and nobody needs to. Now let's connect this back to the accounting context this course is built around, because the slide itself is showing you a workplace version of exactly the same idea. Imagine a manufacturer in Shah Alam that issued 8,400 supplier invoices last year. That complete set of 8,400 invoices is the population. An auditor cannot realistically check all 8,400 of them within a reasonable budget or time frame, so instead the auditor pulls and carefully checks 200 of those invoices. Those 200 invoices are the sample. This slide also introduces some matching notation that you will see again and again throughout the rest of the course. A population has a size, written as capital N, and a mean, written as the Greek letter mu. A sample has its own size, written as lowercase n, and its own mean, written as x bar. A number that describes the population, like mu, is called a parameter, which simply means a fixed, usually unknown number that describes the whole group. A number that describes the sample, like x bar, is called a statistic, which simply means a number we have actually calculated from data we collected. So to anchor this firmly in your mind, population is the whole pot, sample is the spoonful you actually taste. Are you comfortable with that distinction? Good, because the next slide leans on it very directly. Let's go back to that manufacturer in Shah Alam for a moment. The company's true average invoice value, calculated across every single one of those 8,400 invoices, is a parameter. We call it mu. Here is the uncomfortable truth about parameters in the real world. We will almost never know this number exactly, because nobody is going to recheck every single invoice in the entire population just to find out. What we do know, with complete certainty, is the average of the 200 invoices the auditor actually pulled and checked. That known number is x bar, the statistic, and in this case it works out to 4,250 ringgit. The auditor's entire job, in a sense, is to take that known statistic and use it to make an honest, defensible statement about the unknown parameter. Here is an example that might make this distinction click even faster. Think about a detective investigating a crime. The detective never personally watched the crime happen, so the detective does not know with total certainty exactly who committed it. What the detective does have is evidence: fingerprints, witness statements, security footage. The detective uses that evidence, the clue, to draw a conclusion about who the culprit actually is, the truth they are trying to uncover. In exactly the same way, a statistic is the clue, and a parameter is the truth we are ultimately trying to estimate. So remember this rule, because it never reverses. We always use the statistic, the thing we actually measured, to estimate the parameter, the thing we cannot directly observe. We never do it the other way around. Is that clear? Now let's talk about why we even bother sampling in the first place, instead of just checking everything. There are 5 practical reasons we sample instead of checking an entire population, and every single one of them is going to sound familiar to you from real life. The first reason is cost. Checking absolutely everything is expensive, in staff hours, in equipment, in money. The second reason is time. Regulators such as Bursa Malaysia, the company's commission known as SSM, and the tax authority LHDN all set deadlines that a full, exhaustive check of everything would simply blow past. The third reason is physical impossibility. Some populations are so enormous that fully observing every single member of them is not realistically possible at all. The fourth reason is destructive testing. If testing a light bulb's shelf life means burning it out completely, you obviously cannot test every single light bulb on the production line, because then you would have nothing left to sell. The fifth reason is accuracy, and this one surprises people. A small, carefully and thoroughly checked sample often produces more reliable results than a rushed, sloppy attempt at checking everything, because rushing increases the chance of careless mistakes. There is also a professional point worth making clearly here. Auditing standards do not treat sampling as some kind of shortcut or compromise. International Standard on Auditing 530 on audit sampling explicitly recognizes a well-designed sample as a completely legitimate basis for forming an audit opinion. It is not a lesser substitute for checking everything, it is the accepted professional method. Here is an everyday version of the same logic. When your doctor wants to check your cholesterol level, they do not drain every drop of blood out of your body to be thorough. That would obviously be absurd and dangerous. A small, well-drawn vial tells the whole story just fine. Sampling, in other words, is not a corner we are cutting out of laziness. It is a deliberate, well-justified professional choice. Let's look at the actual menu of methods available to us for doing it properly. This is the single biggest dividing line in the entire toolkit of sampling methods, so pay close attention here. Probability sampling means that every single member of the population has a known, non-zero chance of being chosen for the sample. Because we know those chances precisely, we can mathematically measure how much error our sample is likely to carry. Non-probability sampling, by contrast, means selection happens by judgment or by convenience. It is often faster and cheaper to carry out, but we lose our ability to mathematically measure the error involved. Here is a comparison that should make the difference obvious. Imagine a charity raffle where every single ticket is numbered, printed, and tracked in a list, and the winning ticket is drawn completely at random. You can calculate the exact odds of any particular ticket winning. Now compare that to a manager at a small office simply waving over whoever looks free right now to help with the task. There is no list, no tracking, no calculable odds at all for who gets picked. The raffle is probability sampling. The wave-over is non-probability sampling. There are 4 probability sampling methods coming up over the next several slides: simple random sampling, systematic sampling, stratified sampling, and cluster sampling. Let's meet the first one now. Simple random sampling means that every single member of the population has exactly the same chance of being picked, with no exceptions. The recipe is straightforward. First, you build a complete list of the entire population, called a sampling frame, which simply means a numbered list of every single person or item in the group. Then you generate random numbers, and you pull whichever items those numbers happen to land on. In Excel, this is as simple as typing the function RANDBETWEEN with your smallest and largest reference numbers, then copying that formula down a column, and replacing any duplicate numbers that happen to come up. Here's the workplace picture from the slide. An auditor wants to check 15 out of 300 sales invoices. They have Excel generate 15 random numbers between 1 and 300, and whichever invoices those numbers correspond to become the sample. Every single invoice in that group of 300 had an equal chance of being chosen. Think about how a national lottery works, where every number combination has exactly the same odds of being drawn as every other combination. That is the same underlying logic as simple random sampling, just applied to invoices instead of lottery balls. The strength of this method is that it rests on the simplest possible theory and produces unbiased estimates. The weakness is that you need a genuinely complete and accurate list of the whole population to start from, and pure chance might still happen to miss an entire subgroup that matters. Let's move on to method 2, Systematic sampling means picking every KDH item after one single random starting point, where K, called the sampling interval, equals the population size divided by the sample size. Here is the worked example from the slide. Suppose you are auditing 50 out of 1,000 purchase orders. K equals 1,000 divided by 50, which works out to 20. If your random starting point is order number 7, then your sample consists of orders 7, 27, 47, and so on, all the way up through order 987. Think about a security guard at a car park who decides to inspect every 20th car that drives in, starting from a randomly chosen car. It is quick, predictable, and easy to carry out consistently across an entire shift. But here is the real danger hiding inside this method, and it is worth slowing down for. If the population has some hidden, repeating pattern to it, then every KTH item might accidentally share some feature in common. Imagine that, purely by coincidence, every 20th transaction in a company's records happens to fall on a Sunday, perhaps because of how their batch processing schedule works. Your sample, which looks perfectly random on the surface, could secretly turn out to be entirely made up of Sunday transactions. That would be a biased sample wearing a disguise that looks like a random one. Shall we look at method 3? Stratified sampling means dividing the entire population into strata, which simply means subgroups that are internally similar to one another, and then taking a simple random sample inside each one of those subgroups separately, before combining all the results back together. Here's the workplace example from the slide. Picture an audit firm with 850 clients in total, split naturally into 3 groups: large listed companies, medium-sized private companies, and small enterprises. Rather than hoping that one plain random sample happens to cover each size group fairly by sheer luck, the firm deliberately samples 10 large clients, 60 medium clients, and 30 small clients, matching each group's actual share of the total client base. Think about how a school might want to survey student satisfaction by deliberately including students from every single grade level, rather than hoping a purely random sample of the whole school happens to catch a fair number of students from each grade by chance. The strength of stratified sampling is that every subgroup is guaranteed some representation in the final sample, and the results are often more precise than plain, simple, random sampling for the same overall sample size. There is one more probability method left to cover. Cluster sampling means dividing the population into naturally occurring clusters, randomly selecting only a handful of those whole clusters, and then examining absolutely everything inside the clusters you selected. Here's the workplace example. Picture a retail chain with 120 outlets spread across the country. Instead of trying to sample scattered transactions from all 120 outlets, which would mean traveling everywhere, you instead randomly select just 8 whole outlets and check every single transaction inside those 8. Here is the key contrast worth holding on to, because students often confuse stratified sampling with cluster sampling. In stratified sampling, each subgroup is internally similar, almost like sorting laundry by color, and you sample from every single subgroup. In cluster sampling, each subgroup is internally diverse, more like a mini version of the whole population packed into one location, and you sample from only some of those locations, not all of them. Think about a national health survey that wants to study an entire country's diet. Instead of visiting individual households scattered everywhere, researchers might randomly select a handful of entire villages and then survey every single household inside those selected villages. The strength of cluster sampling is that it is cheap and practical when the population is spread out geographically. The weakness is that it is usually less precise than simple random sampling for the same sample size, because everyone inside one cluster tends to be more similar to each other than to the population as a whole. Are you comfortable with that contrast between stratified and cluster sampling? Let's see all 4 methods placed side by side. This slide brings all 4 probability sampling methods together into one summary table, comparing how each one selects items, whether it requires a complete sampling frame, and the strength and weakness of each. I am not going to read every single cell of that table out loud, since you have just heard the full story behind each method explained individually with examples. Think of this slide like a packing checklist you glance at after you have already packed your suitcase. It simply confirms that you have not forgotten anything important. If you remember nothing else from this first half of the lecture, remember this. All 4 of these probability methods share one essential superpower, a known, calculable chance of selection for every member of the population, and that known chance is exactly what lets us mathematically measure the error we expect from our sample. Let's move on to Part B. Welcome to Part B, non-probability sampling. followed by a brand new idea called the sampling distribution. That second half is genuinely the single most important concept in this entire course, so I want you to stay closely with me through what comes next. Sometimes you simply do not have a complete list of the population to work from, or you need a fast answer and cannot afford the setup time that proper probability sampling requires. That is exactly where non-probability sampling earns its place in the toolkit. Remember, non-probability sampling means selection happens by judgment or by convenience rather than by known calculable chance. We do lose the ability to mathematically calculate sampling error with this approach, but the method is still genuinely useful for exploratory work, for targeting audit risk efficiently, and for market research. 4 types are coming up: convenient sampling, judgmental sampling, quota sampling, and snowball sampling. I want you to think of these 4 methods as a different toolbox entirely, not as a lesser or inferior toolbox. A hammer is not a worse screwdriver, it is simply built for a completely different job. Let's walk through all 4 non-probability methods one at a time. Convenient sampling means picking whatever is easiest to reach, with no particular system behind the choice. For example, imagine surveying shoppers at one single mall on one single Saturday afternoon purely because that mall and that day happened to be convenient for the researcher. Judgmental sampling, sometimes also called purposive sampling, means an expert deliberately selects the items they believe will be most informative, based on their own experience and judgment. Here is the workplace example you will probably recognize instantly from your own studies. An auditor who deliberately selects unusually large invoices and related party transactions for closer inspection, because professional experience tells them that is exactly where problems tend to hide. This is precisely how modern risk-based audit sampling actually works in practice. Quota sampling means setting specific subgroup targets in advance and then filling those targets with whoever happens to be convenient to reach. For example, imagine a survey that needs exactly 50 male respondents and 50 female respondents, and the researcher simply interviews the first 50 people of each gender who happen to walk by. Snowball sampling means that existing respondents recruit further respondents from within their own personal networks, much like a snowball that picks up more and more snow as it rolls down a hill, growing larger with every turn. For example, imagine trying to study a sensitive, hidden topic like informal lending practices among small traders, where one trusted contact refers you to the next, because this particular group is never going to appear on any public list you could sample from directly. Are you following the distinction between all 4 of these? Let's compare the 2 entire families of methods directly against each other. Here is another side-by-side table, but this time it contrasts the 2 whole families of methods against each other rather than comparing methods within one family. Probability sampling gives known selection chances for every member, lets us quantify sampling error mathematically, and genuinely generalizes back to the population with calculable confidence. Non-probability sampling gives unknown selection chances, cannot be quantified mathematically, and only generalizes back to the population tentatively at best, but it is considerably faster and cheaper to set up and carry out. Here is a way to think about why neither family is simply better, in some absolute sense. A quick taste test in a home kitchen and a certified laboratory chemical analysis both have a legitimate place in the world. They are simply not used for the same purpose or held to the same standard. You would not send a home cook's taste test to a court of law, and you would not wait 3 weeks for a lab result just to decide if your dinner needs more salt. Is that distinction clear now? Let's talk about a completely different kind of error, one that has nothing to do with which sampling method you chose. This is a distinction that genuinely trips people up the first time they encounter it, so let's go slowly. Sampling error means the natural, expected gap between your sample statistic and the true population parameter, and it exists purely because you only looked at part of the group instead of the whole thing. We write it as x bar minus mu. Here is the most important thing to understand about sampling error. It is not a mistake. It is built into the very nature of sampling itself, and crucially, it is something we can actually measure mathematically, which is exactly what the rest of today's lecture is going to show you how to do. Non-sampling error, by complete contrast, comes from genuine problems in how data was collected or handled. Data entry mistakes, poorly worded survey questions, people refusing to respond, or someone misreporting information. Here is the surprising part. Non-sampling error can happen, even if you somehow manage to survey or check absolutely everyone in the entire population, a full census of every single person. Let's look at the specific numbers from the slide. 200 sampled invoices produce an average of 4,250 ringgit against a true population mean of 4,180 ringgit. That 70 ringgit gap is ordinary, expected sampling error, nothing has gone wrong. But suppose that 30 of those invoices were mistakenly keyed into the system as 4,200 ringgit when they should have read 2,400 ringgit. That is non-sampling error, a genuine data entry mistake, and it quietly contaminates and biases every single calculation that follows from it. Here is a way to keep the two firmly separated in your mind. Sampling error is like a slightly imprecise kitchen scale that naturally jitters a gram or two in either direction every time you weigh something. That is just normal measurement variation. Non-sampling error is like someone accidentally typing the wrong number into a recipe entirely, using 1 cup of salt instead of 1 teaspoon. One is expected and harmless if you account for it properly. The other is a genuine mistake that can ruin the whole dish. Is that difference clear? Now let's meet today's single most important idea. This is the single most important idea in today's entire lecture, so let's go slowly and carefully through it, one piece at a time. Imagine, purely as a thought experiment, that you draw a random sample from a population and compute its mean, and you call that mean x bar 1. Then you put everything back exactly as it was, draw a completely new random sample, and compute a second mean, x bar 2. You repeat this process thousands and thousands of times, drawing sample after sample, each time computing a new average. Now imagine collecting every single one of those x-bar values and plotting how often each particular value shows up. That resulting picture is called the sampling distribution of the sample mean, which simply means the probability distribution describing every possible value that x-bar could take across endless repeated sampling. Here is the conceptual shift you need to make right now, because everything afterward depends on it. X-bar is not one single fixed number sitting still. It is itself a random variable, changing every single time you draw a new sample. So if you want to say something honest and defensible about the unknown population mean mu, based on just one single sample mean x-bar that you happen to calculate, you first need to understand how x-bar behaves across all of those many possible samples you could have drawn instead. Let's build some everyday intuition for this before we touch the workplace version. Imagine you and 4 friends each independently grab a different handful of jelly beans from the very same large jar, and each of you weighs the average weight of the beans in your own handful. Your 5 average weights would almost certainly not be identical to each other. Pure chance guarantees some variation. But they also would not be wildly, randomly different from one another either. They would tend to cluster fairly close together, somewhere near the true average weight of a bean in that jar. That clustering pattern you can picture in your head is exactly what we are about to describe precisely using numbers. Now here is the matching workplace picture from the slide. If 5 different auditors each independently sampled 200 different invoices from the very same company, each auditor would end up with a slightly different average invoice value. The sampling distribution is the mathematical description of the entire pattern of those 5 or 5,000 possible averages, not just one of them in isolation. Does the underlying idea make sense to you, even before we attach any formulas to it? Good, because that is honestly the hardest part. Let's put some actual numbers around it now. There are 3 describable properties of this sampling distribution, and we are going to take them one at a time. The first property concerns the mean. On average, across every single possible sample you could ever draw, x-bar equals mu, exactly. We describe this by saying that x-bar is an unbiased estimator, which simply means it does not systematically run too high or too low over the long run. It is centered correctly on the truth. The second property concerns the spread, and this spread has an important name of its own, the standard error. The standard error simply means the standard deviation of the sampling distribution itself, and it is calculated as sigma divided by the square root of n. Here is the practical consequence worth remembering. A bigger sample size produces a smaller standard error, which means a more precise estimate of the population mean. The third property concerns shape, and that is exactly where the central limit theorem comes in, which we will cover in detail in just a moment. Let's build some intuition for the spread property first, using 2 examples, one from daily life and one from the workplace. Think about a 50-person sales team's average commute time into the office each morning. That average swings far less from day to day than a single one-person team's commute time would, because averaging across many people smooths out the unusually good days and the unusually bad days, leaving a steadier overall number. In exactly the same spirit, A single day's weather forecast can be quite far off the actual temperature, but the average accuracy of weather forecasts across an entire month tends to be far steadier and more reliable than any one single day's forecast taken alone. Are you comfortable with the mean property, the spread property, and the promise of a shape property still to come? Let's see exactly how much that spread actually shrinks as sample size grows. Let's work through a numeric illustration together. Picture a population with a true mean of 12,000 ringgit and a standard deviation of 3,000 ringgit. Now watch carefully what happens to the standard error as the sample size n climbs through four specific values: 25, 100, 400, and 900. At a sample size of 25, the standard error works out to 600 ringgit. At 100, it drops to 300 ringgit. At 400, it drops further to 150 ringgit. At 900, it drops to exactly 100 ringgit. Notice the pattern hiding in those four numbers. Every single time the sample size quadrupled, the standard error was cut exactly in half. That relationship has a name, the square root law, and here is why it happens. Because the standard error formula divides by the square root of n rather than by n itself, you must quadruple your sample size just to cut your error in half. Doubling your sample size alone does not get you anywhere near double the precision. Here is why this matters enormously for anyone planning real audit work or any kind of research budget. Precision gets expensive very quickly under this law. Doubling your sample size does not double your precision. It only buys you roughly 40% of the way toward halving your error. Here is an everyday version of the exact same diminishing returns pattern. Think about smartphone camera resolution over the years. The very first jumps in camera megapixels made an obvious, dramatic, visible difference in photo quality. But doubling an already very high resolution today gives you a far smaller visible improvement, while creating a much bigger file to store. You are paying more for less and less extra benefit each time, and that is precisely the same diminishing returns curve we just saw with sample size and standard error. Let's head into part C, which is really the heart of today's entire lecture. Welcome to part C, the central limit theorem, and our very first confidence intervals built using the Z distribution. Take a breath here, because this section is the payoff for absolutely everything we have built up to this point. Here it is, stated in full, so listen closely. This is the central limit theorem. For a sufficiently large sample size n, the sampling distribution of x bar is approximately normal, that same bell-shaped curve we studied last week. It is centered at mu, the true population mean, with a standard deviation of sigma over the square root of n. Here is the genuinely remarkable part of this theorem. This holds true regardless of what shape the original population's data actually has. The raw underlying data could be lopsided, lumpy, or oddly shaped in any way you like, and the theorem still works perfectly fine once you are averaging across a large enough sample. We standardized this sampling distribution in exactly the same way we standardized individual values last week, just swapping in the sampling distribution's own mean and its own standard error instead. Z equals x bar minus mu, divided by sigma over the square root of n. Here is an everyday picture of why averaging creates this smoothness. A single day's traffic on the highway during your commute can be a complete nightmare, unpredictable and chaotic. But your average commute time across an entire month is far steadier and more predictable than any single day's trip considered on its own. Averaging itself is what creates that smoothness. It cancels out the unusually bad days against the unusually good days. The matching workplace picture from the slide makes the same point. Individual daily customer complaint counts at a company can bounce around chaotically from day to day, but the average number of complaints across a full month settles into a smooth, far more predictable pattern. Does that land for you? Good. Now we need to pin down exactly what sufficiently large actually means in numbers. The honest answer is that it depends on the shape of the population you are sampling from. If the population itself is already perfectly normal in shape, then x bar is exactly normal for any sample size at all, even an extremely small sample size like n equals 2. If the population is roughly symmetric but not perfectly normal, a sample size of 15 or more is generally considered enough. If the population is skewed, meaning lopsided, with a noticeably longer tail stretching out on one side, you typically want a sample size of 30 or more to feel safe. Here is why this particular rule matters so much in our field specifically. Most financial populations you will encounter in practice, things like invoice values, salaries, or transaction sizes, tend to be right skewed, with a long tail of unusually large values stretching out to the right. And in real practice, we rarely know the population's exact shape in advance anyway. The central limit theorem hands us a genuinely useful safety net here. Once your sample size n reaches 30, you can treat x bar as approximately normal regardless of whatever shape the underlying population actually has. That single fact is what unlocks every confidence interval and every hypothesis test for the remainder of this entire course. Think about a bridge's posted weight rating. You, as a driver, do not need to know the exact weight of every single vehicle that has ever crossed that bridge. You just need one simple rule of thumb threshold that tells you when it is safe to trust the bridge. The number 30 plays exactly that same role for us here. It is our rule of thumb threshold for trusting the bell curve shape. Are you comfortable with the reasoning behind why 30 specifically gets used? Let's apply all of this to a real set of numbers now. Let's work through this together, slowly and one step at a time. A firm's mean audit adjustment is mu equals 850 ringgit, with sigma equal to 200 ringgit, and the underlying population is known to be right skewed. An auditor samples 36 adjustments. What is the probability that the sample mean turns out to exceed 920 ringgit? Step 1. Our sample size n equals 36, which clears our threshold of 30, so the central limit theorem allows us to treat x bar as approximately normal here, even though the underlying population itself is skewed. Step 2. The standard error equals 200 divided by the square root of 36. The square root of 36 is exactly 6. So the standard error equals 200 divided by 6, which works out to roughly 33.33. Step 3. Now we standardize. Z equals 920 minus 850 divided by 33.33. That numerator is 70, so Z equals 70 divided by 33.33, which works out to roughly 2.10. Step 4. Looking this value up in the Z table, the area beyond 2.10 is 1 minus 0.9821, which equals 0.0179. So there's only about a 1.8% chance of observing a sample mean above 920 ringgit if the true mean really is 850 ringgit as assumed. An auditor who actually observes a sample mean that high should treat that result as a meaningful warning sign worth investigating further, since it would be a fairly unusual outcome if nothing unusual were actually going on. I would encourage you to walk back through this exact calculation again on your own once this lecture finishes, because this 4-step structure is the template you are going to reuse again and again for the rest of today. Ready for the next idea? A point estimate simply means a single best guess number, like saying x bar equals 4,250 ringgit. Here's the problem with stopping there. That single number is almost never exactly equal to mu, and on its own, it gives you no sense at all of how close it might actually be to the truth. An interval estimate, which is usually called confidence interval, fixes that problem. A confidence interval simply means a range of plausible values paired together with a confidence level attached to that range. Instead of giving one single number, we give a whole range. We would say something like, we are 95% confident the true mean lies somewhere between 4,100 and 4,400 ringgit. Here is an everyday comparison that should make the difference obvious immediately. A point estimate is like a weather forecaster simply saying, tomorrow will be 28 degrees. A confidence interval is the far more honest version that meteorologists actually use in practice, something like between 26 and 30 degrees, with high confidence. Or think about guessing someone's exact age, purely from a photograph. Guessing one single exact number is a point estimate, and you would probably be wrong. Guessing somewhere between 30 and 35 years old is an interval, and you are far more likely to actually be right. Which approach sounds more genuinely useful to you? Exactly, the interval. Let's learn how to build one properly. Here is our first formal recipe for building a confidence interval. You use the z-based interval whenever sigma, the population standard deviation, is already known to you, or whenever your sample size is 30 or larger. The formula is x bar plus or minus z alpha dash over 2 multiplied by sigma over the square root of n. That second piece of the formula has its own name, the margin of error, which simply means how far above and below x bar the entire interval stretches in each direction. There is a quick reference table of critical values worth memorizing here. 90% confidence uses a z-value of 1.645. 95% confidence uses 1.96. 99% confidence uses 2.576. I would circle that middle number 1.96 in your own notes, because 95% confidence is the default level almost everyone reaches for in practice, unless they have a specific reason to choose otherwise. Have you got those three numbers written down somewhere? Let's plug them straight into a real problem now. An auditor samples 64 supplier invoices. Sigma is known to be 800 ringgit, and the sample mean X bar turns out to be 4,250 ringgit. Let's build a 95% confidence interval together, step by step. Step 1. For 95% confidence, our Z alpha over 2 value is 1.96, exactly as we just memorized. Step 2. The standard error equals 800 divided by the square root of 64. The square root of 64 is exactly 8, so 800 divided by 8 equals exactly 100. Step 3. The margin of error equals 1.96 multiplied by 100, which equals 196. Step 4. The interval is 4,250 plus or minus 196. That gives us a range from 4,054 up to 4,446. In plain, ordinary English, we are 95% confident that the true average invoice value for this entire population falls somewhere between 4,054 and 4,446 ringgit. And we built that entire claim from just 64 invoices out of however many thousands actually exist. Were you able to follow each step there? Let's see what happens when we deliberately change the confidence level. Let's use the exact same data as before and change only the confidence level to see what happens to the interval. At 90% confidence, the margin of error is 164.5, giving an interval from 4,085.5 up to 4,414.5. At 95% confidence, the margin is 196, exactly as we just calculated. At 99% confidence, the margin balloons all the way up to 257.6, stretching from 3,992.4 up to 4,507.6. Notice the trade-off hiding in those three numbers. Higher confidence always means a wider interval. You are essentially buying extra confidence by paying for it with reduced precision. Here is a way to feel that trade-off intuitively. A weather forecaster could technically say they are 99% confident that tomorrow's temperature will fall somewhere between minus 10 degrees and 50 degrees. That statement would be technically true, but it would also be completely useless to you, precisely because the range is so enormously wide. Tightening that range down to something actually useful always costs you some confidence in return. Does that trade-off feel intuitive to you now? There is one more subtlety left about what being confident even really means, and it is worth slowing down for. This particular point trips up even experienced working professionals, so listen closely here. Mu is a single fixed number out there in reality. It does not move around, and it does not change depending on what we believe about it. A confidence interval that you have already built either does contain that fixed value of mu, or it simply does not, and there is no probability involved at all anymore once the interval has actually been calculated from your data. So what does 95% confident actually describe? It describes the long-run reliability of the procedure you used to build the interval, not this one specific interval sitting in front of you right now. It means that if you repeated the entire sampling process many times over, about 95% of all the intervals you would build that way, across all those repetitions, would end up containing the true value of mu. Here's a sentence I want you to never say out loud because it sounds right but is actually wrong. There is a 95% probability that mu lies inside this interval. That sentence is incorrect. Because mu is not a random quantity, it is a fixed number. We simply do not happen to know its exact value. Here is a workplace picture that should help this click. Imagine 100 different auditors, each one independently sampling their own set of invoices, and each building their own separate 95% confidence interval. Roughly 95 of those 100 intervals will actually capture the true mean inside them. Roughly 5 of those intervals will miss it entirely, purely through bad luck in which invoices happen to get sampled, and critically, there is no way to know in advance which 5 of the 100 auditors got unlucky. Here is an everyday version of the same idea. It is similar to a particular brand of umbrella advertising that it works 95% of the time in heavy rain. That is a statement about the umbrella's overall track record across many storms tested in a lab. It is not a guarantee about whether the specific umbrella in your hand right now, today, in this particular storm, is actually going to hold up. That distinction genuinely deserves a moment to properly sink in before we move forward. Let's move into Part D. Welcome to Part D. What to do when sigma is completely unknown, how to choose a sample size on purpose ahead of time, and how to get Excel and SPSS to handle this arithmetic for you automatically. Here is an uncomfortable truth about real audit work. In practice, you almost never actually know sigma in advance. Up until this point in the lecture, we have quietly been assuming we knew sigma, which was a convenient simplifying fiction to help the ideas land more easily. In real life, we instead estimate sigma using the sample standard deviation, which we call S. That substitution, swapping S in for sigma, especially when your sample is small, changes the underlying mathematics in an important way. The statistic x bar minus mu divided by S over the square root of n no longer follows the standard normal distribution exactly the way it did before. Instead, it follows something called the student's t-distribution, with degrees of freedom, which simply means a count, here equal to n minus 1, tracking how much genuinely independent information your particular sample actually carries. The t-distribution looks broadly similar to the normal curve, symmetric and bell-shaped, but it is flatter in the middle and has heavier tails out at the edges, reflecting the extra layer of uncertainty that comes from estimating sigma instead of simply knowing it outright. As your sample size n grows larger, the t-distribution tightens up and gets closer and closer to the z-distribution, and by around a sample size of 30, the two are nearly identical to each other. Here is an everyday picture for this. Think about the difference between trusting a brand new employee's estimate of how long a task will take versus trusting a 20-year veteran's estimate of the same task. The newer employee's estimate carries more built-in uncertainty, simply because they have less experience to draw on, so you would naturally want to widen your safety margin around whatever number they give you. In exactly the same spirit, a secondhand description of how bad the traffic is right now deserves a wider error margin in your own planning than an actual live traffic report would. Are you comfortable with why the t-distribution needs to exist at all? Let's pin down exactly when you should reach for each one. Here is the decision rule, and it is genuinely worth memorizing properly. If sigma is known, you use z, regardless of how large or small your sample size happens to be. If sigma is unknown but your sample size n is 30 or larger, you can still safely use z, simply substituting s in for sigma. If sigma is unknown and your sample size n is below 30, you must use t instead, with degrees of freedom equal to n minus 1. The t-based confidence interval formula mirrors the z-based one almost exactly, just swapping in t alpha over 2 and s in place of z alpha over 2 and sigma x bar plus or minus t alpha over 2 at n minus 1 degrees of freedom multiplied by s over the square root of n. Here is an image that might help this stick. Think about a tailor cutting a suit. Working from your exact, precisely recorded measurements, the tailor can cut the fabric close and confident with very little wasted material. Working instead from only a rough estimate of your size, the tailor deliberately leaves some extra fabric as a safety margin, just in case the rough estimate was a little off. The t-distribution functions exactly like that built-in safety margin, automatically added whenever your information about the population is thinner than you would like. Are you ready to actually read a real t-table? The t-table has two dimensions to navigate. The rows represent degrees of freedom, and the columns represent tail area, which simply means the probability cut off in one single tail of the distribution, for example 0.025, for a typical 95% two-tailed confidence interval. Here is a worked example. For 95% confidence with a sample of 20, your degrees of freedom is 19, and your tail area is 0.025. Looking those two values up in the table gives you a t-value of 2.093. Notice that this t-value is larger than the matching z-value of 1.96 that we used earlier. The t-based interval will always come out a little wider than a z-based interval for the same confidence level, and that is a direct, visible consequence of having to estimate sigma using s instead of knowing it outright. Reading a t-table is a lot like reading a tide chart at a harbor. You cross-reference one piece of information, the day, which plays the role of degrees of freedom here, against another piece of information, the time, which plays the role of tail area, in order to find the one number you actually need. It can feel intimidating the very first time you try it, but it becomes second nature almost immediately after that. Are you ready for a complete worked example using everything we have covered? A senior auditor samples 16 audit completion times and finds X bar equals 42 hours, with S equal to 8 hours. Let's build a 95% confidence interval together. Step 1. Sigma is unknown here, and n equals 16, which is below 30, so we must use t with 15 degrees of freedom. Step 2. Looking in the t-table, t at 0.025 with 15 degrees of freedom equals 2.131. Step 3. The standard error equals 8 divided by the square root of 16. The square root of 16 is exactly 4, so 8 divided by 4 equals exactly 2. Step 4. The margin of error equals 2.131 multiplied by 2, which equals 4.262. Step 5. The interval is 42 plus or minus 4.262, giving a range from 37.74 hours up to 46.26 hours. In plain English, we are 95% confident that the true mean audit completion time falls somewhere between 37.74 and 46.26 hours. Notice that this interval is wider than a z-based interval would have been with otherwise identical numbers. That extra width is the t-distribution's built-in conservatism showing up in real, concrete numbers. Let's flip the entire question around now. So far in today's lecture, we have always asked the same basic question. Given a particular sample size, how wide does my resulting confidence interval turn out to be? This slide flips that question completely around. Given how narrow I actually need my interval to be for it to be useful, how large a sample do I need to collect in the first place? Solving the margin of error formula backwards gives us n equals the quantity z alpha dash over 2 multiplied by sigma divided by the margin of error e with that entire quantity squared. Here is a worked example. Suppose you want to estimate the true mean invoice value to within 50 ringgit at 95% confidence using a pilot estimate of sigma of roughly 800 ringgit. 1.96 multiplied by 800 divided by 50, then squared, works out to roughly 983.5. Here is a rule that matters every bit as much as the arithmetic itself. You always round up, never down. We need a sample size of 984, not 983. Rounding down would quietly leave you slightly short of the exact precision you originally promised to deliver. Here is an everyday version of this same backwards logic. A market research firm typically decides first how much error it is willing to tolerate, and only then calculates backwards to find the sample size that achieves that tolerance, rather than simply guessing a sample size first and hoping the resulting precision happens to be good enough. Are you comfortable working backwards like this? Let's get practical and look at the software side of all this. Here is a quick reference table of the Excel formulas you will actually use for this kind of work. Average gives you X bar. STDEV.S gives you the sample standard deviation S, and that S in the function name genuinely matters because it tells Excel you are working with a sample rather than an entire population. Count gives you N. For the margin of error itself, the function confidence.t takes your significance level, your sample standard deviation, and your sample size and hands the margin of error straight back to you. You then add and subtract that margin from your average to get the upper and lower bounds of your interval. If you are working in Z territory instead, because sigma is known or your sample is large, you simply swap confidence.t for confidence.norm, and everything else about the process stays exactly the same. This is genuinely worth a screenshot for your own personal notes. Let's compress today's 7 big ideas down into one tight summary. We separated a population from a sample and a parameter from a statistic. We covered 4 probability sampling methods: simple, random, systematic, stratified, and cluster, and 4 non-probability methods: convenience, judgmental, quota, and snowball. We discovered that X bar itself behaves like a random variable, with its own entire sampling distribution attached to it. We stated the central limit theorem. Once your sample size reaches 30 or more, X bar is approximately normal, centered at mu, with a standard error of sigma over the square root of n. We built confidence intervals using z whenever sigma is known or the sample is large, and using t whenever it is not. And finally, we learned how to work backwards from a target margin of error to figure out the exact sample size we actually need to collect. Here is the single thread running through every one of those 7 ideas. A sample statistic is just one draw out of an entire distribution of possible draws you could have gotten instead. A confidence interval is our honest, mathematically grounded way of admitting exactly how much that one particular draw could plausibly have differed from the truth.